In this video, we're going to look at parametric integration. So far, we've looked at integrating Cartesian equations where y has been a function of x. When this has been the case, we've simply said now the integral of y dx. What we're now going to do is consider a pair of parametric equations. So what we might have is x is equal to t plus 2 and y is equal to t squared. Both x and y are functions of t. So before y was a function of x, now x and y are functions of t, and t is the parameter. So this is an independent variable now, and we're expressing x in terms of t and y in terms of t. Now if I wanted to integrate, what I could do is go ahead and eliminate the parameter here and express this in a Cartesian equation. So let's go ahead and try and do this. So what we could do here is say, well, if x is equal to t minus 2, then x minus 2 is equal to t. We know that y is equal to t squared, so y would be equal to x minus 2 all squared. So I've eliminated the parameter here. So t, the parameter, has been eliminated, and we now have a Cartesian equation. So what I could do is go ahead and integrate this and find the area trapped under the curve between two limits. So let's draw a quick sketch, and it will look something, give or take, like so. So it's going to be a parabola, it will be symmetric, and then it will touch now the x-axis at this point. So let's say I wanted to find the area trapped under the curve. So this is going to be the point 2, and this will be the point 4. So if I wanted now to find that, let's just put that up and put this point just here. I wanted to find out a shaded area. What I could say then is I could take the integral from x is equal to 2 to x is equal to 4 of this function. So I could now write that the area was equal to the integral from 2 to 4 now of x minus 2 all squared dx. So we've met functions like this before, and they're fairly straightforward to integrate. So what we can say then is the area will be 1/3 the quantity x minus 2 to the power of 3, and we're interested now in evaluating this between the limits of 2 and 4. So if I now sub that in, what I've got here, the area is going to be equal to 1/3. If I now put in 4, 4 minus 2 is 2, 2 cubed is 8. If I put in now 2, 2 minus 2 is 0, so I subtract away 0. So we can see from this now that the area trapped under the curve between now the x coordinates 2 and 4 is going to be 8/3 units squared. So what I've done here is converted from parametric form, where we have x as a function of t and y as a function of t, now to Cartesian form, where y is a function of x, and we've integrated. Now, sometimes it won't be convenient for us to do this, and we can use parametric integration to find the area under a curve. As a result of a chain rule, what we can say is the following. We can say now that it will be the integral of y dx dt between t1 and t2. We will either be given now t1 and t2, or we will have to find it. So let's go ahead and work with this particular case and take now x is equal to t plus 2 and y is equal to t squared. So what I'm going to do is show that these areas are going to be the same whether we integrate parametrically or in Cartesian form. So let's first look at the limits. I've got now t1 and t2. Let's consider when x is equal to 2. So when x is equal to 2, we can say now that t plus 2 is equal to 2. Therefore, we can say that t would be equal to 0. So all I've done is simply sub that in. Now, if x is equal to 2, t plus 2 is equal to 2, therefore t is 0. When x is equal to 4, we can say now that 4 is equal to t plus 2, therefore we can say that t will be equal to 2. So what I'm now looking at is the integral from from 0 to 2, let's write that down, from 0 to 2 of y dx dt. So let's go ahead and write that down from now 0 to 2 of y. Now y is t squared, so I'm going to have t squared dx dt, and we're integrating with respect to t. So I've altered the limits. What I now need is dx dt. Now I know that x is equal to t plus 2, therefore dx dt, the derivative of x with respect to t, is 1. So all I'm going to do is now sub that in. So I'm looking at the integral from 0 to 2 of t squared multiplied by dx dt, which is just 1, and that will now give me the integral now of t squared dt from 0 to 2. So if we go and do that, what we're going to have now, the area will be equal to 1/3 t cubed, and I'm interested in this now from t is equal to 0 to t is equal to 2. So the area is going to be 1/3. If I sub in 2, 2 cubed is 8. If I sub in 0, that's 0. And we end up with exactly the same. So we get now 8 over 3. Let's write 8 over 3 units squared, as we did in Cartesian form. So all we've done is simply now use parametric integration to show that these two areas are the same. It won't always be convenient for you to switch from parametric to Cartesian. If you can, it's an awesome tool for checking that you have done it correctly either way round. So if you wanted to go back to Cartesian with this and say, well, I'm not sure if that's right, you can eliminate the parameter t, consider now the limits in terms of x, and go ahead and find that area. This too extends to the volume of revolution. So we can say the volume is given now as pi multiplied by the integral of y squared dx dt dt, where t is our parameter. Generally we have t or theta, so if we had theta it would be dx d theta d theta. So there we go, some basic work looking at parametric integration. With this, sometimes you'll have now multiple choices of t, and you just have to be careful to choose the right one. So what we're going to do now is look at a couple of examples of this.